Thanks. So I'm Brandon Hathaway. I'm going to be talking to you about the work that we're doing here with Sunvapor on our hybrid oil field water desalination installation, or Howdy, as we refer to it. So I'm the Director of Engineering here at Sunvapor. We also have Philip Gleckman as well available. He's our CEO. So jumping into the presentation. The problem, I think we're all already familiar with, is the produced water that's being developed or generated along with our oil production here. And that's leading to some issues with seismicity in the region, as well as the need for the water that could potentially be produced, with some projections showing that Texas is facing a 7 million acre foot shortage of water by 2070, and that 51 million people could have less than half the water supply they need during a drought of record. And so there's a significant desire to get some useful clean water out. And one of the big challenges of getting clean water from the Midland Basin is the hypersalinity of the water, which we're targeting water with TDS levels in the 120 to 130 gram per liter range. And so this is what we're hoping to process into a clean stream of distillate, along with then waste stream that can be disposed of, reducing the total volume that's getting put in the ground to help those problems and provide water available for reuse. And so getting into how we're planning to go about this work is through a hybrid desalination process that we've patented. And so we're aiming to recover, similar to what was mentioned before, about 50% of the wastewater for beneficial reuse. Depending on how high we push the TDS, potentially we might be able to get to higher concentrations if we get comfortable with it, to just near saturation. So right now targeting 260,000 ppm, but could potentially push that to 280, 300 range if we find we get stable concentrates without the precipitation of any side species. So the way we'll go about this in our hybrid process is a two-step process where we're using solar thermal energy to generate steam that will drive a first topping thermal process using a falling film evaporator. So that will use our steam at higher temperatures to take our brine to the maximum concentration that we plan to get to. And as a side product of that process being driven with steam, there's going to be excess thermal energy available that we're going to run to then a lower temperature membrane distillation process that handles the lower concentrating portion of the process. And so our thermal energy cascades down from our solar steam through the evaporator process and to the membrane distillation process, whereas the brine concentrates up through the processes, initially coming in raw after being pre-treated, passing through the membrane distillation process into our evaporator for final concentration. And so the benefits of this approach is that we're generating our steam using, for the pilot, mostly solar thermal energy, and for larger systems, we could plan to run that with a significant solar fraction of solar energy. And that provides us thermal energy input with no greenhouse gas emissions or air pollution side effects from the generation of that thermal energy. And so with the addition of thermal energy storage sized appropriately, we'll be able to have thermal energy available to run the process after sunset as well. So continuing to drive our cycle long after the sun goes down to increase that solar fraction beyond when the sun is even up. So we managed the unique problematic species that exist in these streams with the pre-treatment and post-treatment processes, as would be expected. And so the pre-treatment is mainly dealing with taking out any residual surfactants that might be present, iron and sulfates and organic materials. And so that's handled upstream before the water is processed through our desalination process. And with the thermal process, you might have some volatiles that get carried through. And so then those volatile species would be polished out with our post-treatment steps. So to show you a simplified process flow diagram, this shows essentially what was just described there as our hybrid process. It's kind of structured top to bottom with our three subcomponents. We've got a solar steam generating process where we are producing and storing solar thermal steam in our steam accumulator. That steam is provided into a thermal vapor recompression process that's providing the heat input to an evaporator here. So that is taking our evaporated our vapor, recompressing it to provide the heat input to that process for a regenerative system that is fairly high efficiency, and then a side stream of that vapor, the excess portion, That is then brought down into a condenser here that is being used to heat up our brine stream that is passing through a membrane distillation process on our bottoming portion of the process. And so again, that's the thermal energy cascade that I described before, where our brine is coming in and is being processed at the low temperature membrane distillation process first, brought up to moderate concentrations that are still very safe for membrane distillation processes before being blown up into the evaporator at higher concentration, brought up to near saturation and discharged. So brine flowing up, thermal energy flowing down. And so this cascading approach gives us very high thermal efficiency. We're able to use essentially the thermal energy twice as it passes through our process at two different temperature scales. We're able to separate our processes according to the concentrations they're most comfortable at. So we're able to avoid scaling issues with the membrane distillation process by keeping it in operation at these lower concentrations. And then the evaporator process, which is more robust and is able to handle the high concentrations, we're able to reduce the size of that, keep its capacity smaller by having the membrane distillation process take care of the easy work and using the evaporator just to do the final portion of concentration. So that gives us an optimization that gives us a real efficient approach here by hybridizing between these two processes and letting them each sort of work where they are most successful at operating. So we've got some design validation that's been carried out as well. During an earlier portion of our project development, we tested out the membrane distillation process using actual produced water samples that we shipped from our team's from our project site that we are now building at. And we had a partner laboratory set up at the University of Southern California where they tested under a lot of conditions and verified an appropriate pre-treatment process that allowed us to get up to our desired concentration for the MD process, about 180,000 parts per million, and we're able to operate consistently for about a month straight without issues related to scaling. We did some tests where we brought up to full concentrations and tried some extreme conditions to validate why we wouldn't necessarily want to go to higher concentrations, leading to the image you see there on the right side where we found the conditions that would trigger scaling. And so we've kind of designed our process to keep us away from those concerning conditions and operate where we're comfortable and where we saw good, consistent performance long term without scaling issues. We've also validated the thermal portion of our process. The image you see behind me is actually a parallel version of our solar thermal collection system. It's similar to the one that's being built right now in New Mexico, and this one exists in the Imperial Valley in California. And the large vessel behind me is actually our thermal storage vessel at that project site. And so we validated that heat collection system, worked out the kinks that we know how it's going to operate. And so we are deploying a very similar version in our project site in New Mexico, and we'll be able to build upon that tested technology and that validated performance that we've seen previously to run this pilot system. Let's see. So for the pilot system then, the metrics that we're targeting are shown here. This being a thermal process, our specific energy consumption, when you look at the heat, is a large number than you see for electrical heat consumption or for electrical power consumption. But being thermal energy, it's of course lower exergetic value. And so it's a lower grade energy, easier to obtain from sunlight. So we're looking to target about 175 kilowatt hours of thermal energy per cubic meter of distillate that we produce. Whereas the electrical consumption that's consumed mainly just for driving pumps and our control system, that's going to be pretty low at about a little more than 2.5 kilowatt hours of electrical power per cubic meter of distillate. With that input, we're targeting a distillate water recovery of around 50%. So 51 is kind of the design point with our comfortable, safe ranges of concentration. And depending on how performance looks, we might try pushing to higher concentrations and be able to squeeze that maybe closer to the 55-60% range as we get to higher concentrated outputs. But of course, we want to keep that concentrate liquid still, because the end fate for the concentrate would be to still be injected downhole just at about half the volume of the original in-feed volume. For our distillate, we have some goals here in terms of its quality. We're looking at producing a TDS in our distillate that's less than 300 parts per million. The lab scale with the MD process, we were looking pretty consistently around 100 or so parts per million. And so we think, over the course of an annual operating process, we shouldn't have that creep much higher. The evaporator output should also be consistently low. So we think that's a pretty easy target to hit. And then for the volatiles that would carry over, those would potentially come in the form of total organic content or the total ammonia that might be present. And so for those, we're targeting with our polishing process to get down to sub part per million for any organics and to get the ammonia potentially down to the sub parts per million range to make these distillate available for a lot of different possible reuse applications. Depending on what the reuse application is, there are some where it's not as concerning about, say, the ammonia levels if it were to be reused in industrial processes. And so we may be able to relax that. But our goal is to show that we produce distillate that is flexible and would be available for a lot of different processes. So we're keeping the goals pretty tight for the pilot metrics initially. So now we can show you the current state of affairs for the project. The site plan for our pilot is shown here. We've got a zoomed out satellite view of the actual location. It's just outside of Loving, New Mexico, just off the Potash Mines Road, where NGL has a saltwater disposal well that's in operation. And if we zoom in around the wellhead, which is shown right here, and where their vehicles currently handle, they've got a tank farm that is performing some separation processes on the water. And we've set up our plant down just to the south of that. We've got our solar thermal collector set up, which takes up the largest portion of the footprint, and then a balance of plant equipment pad and a mobile office. So on the equipment pad is where we'll be building out the actual consumers of the thermal energy collected by the sunlight. So our steam generating system and the two distillation processes. Here's some photos of the site taken from just earlier this year, just after we got the solar collectors installed. So they're set up here in the foreground. In the background, you can see the mobile office that will be used to hold the control system, as well as for our work while we're on site. And then the pad right in between the two, shown here, zoomed up. Here it is with just the first pieces of equipment that have arrived. So we've got our steam accumulator there, uninsulated, waiting to go. And next to it is the condenser portion that will be used for heating up our brine. We'll additionally have our evaporator column erected just in the foreground a little further here. Cooling tower that will be used for final waste heat rejection after the MD process, and our MD processing, and our pre-treatment train will all be found on this one pad here that will be located on our site. Well, I'd like to point out that this is kind of the last step for us in the Solar Desalination Prize. We are a finalist in that competition that's been sponsored by the U.S. Department of Energy. And so we've passed through the initial design reviews associated with the earlier steps, and now we're looking to get our pilot up and running so we can get our performance metrics and see if we can get a good report in for the final stage of that Solar Desal Prize. So I want to point out our association with that. And then we'd also like to make note of the funds that have been awarded that have made this project able to go forward here from the New Mexico Economic Development Department. So that's been what really kicked us off into getting the plant built there. And our partners, it'll be important to point out as well, include NGL Energy Partners. And so they're actually supplying the land. They're our site host. They'll be supplying the water and have been very helpful working with us to get the pilot up and running. And then we're collaborating with various universities as well, including the University of New Mexico. And so they're working with us on doing membrane characterization and analysis of the performance of our membrane system. Southeast New Mexico College is teaming with us. They're going to be providing essentially technicians who will be operating the system over the course of the year. And return, they're essentially getting workforce training opportunities. So developing the workforce of people who could operate these produced water treatment systems and gain familiarity with a lot of the basic industrial equipment operations and maintenance that's necessary for running these systems. So we're happy to participate with them. And of course, New Mexico State University is going to be involved with doing the water quality analysis and seeing how clean our distillate is, what fine tuning we might need for a process to hit our goals. And we're looking forward to seeing the results of that as well. I think that completes the presentation. So our CEO's contact information is available here, so you can be reached out to for any questions outside of this time. Otherwise, if there's any questions you have now, we can discuss them.